Welcome to BKW Physics. I'm Mr. McConley, and today we're switching up topics. We're going to talk about waves. Wave motion. And I first want to start with a quote from Leonardo da Vinci, which he quoted around the year 1500. He said, quote, "The impetus is much quicker than the water, for it often happens that the wave flees its place of creation while the water does not." And that statement will make more and more sense as we go through this chapter, but basically what he was saying is, if you drop a rock in the water, the wave moves away, but the actual water just goes up and down and remains where it started. And if you think about that statement for a while, you'll realize that waves, that's the way waves work. They pass through a material, they disturb the material, but they don't actually take the material and move it forward. Okay? And if you can wrap your mind around that one, it's really going to help as we move forward. So, I'm going to take us through some basic knowledge about waves. And we'll start with a definition. A wave is a vibratory disturbance that propagates through a material or space, which is a lot like Leonardo's quote. A wave transfers energy, but it does not transfer the mass. Okay? Again, that's what Leonardo said. Now, as we get into some different words that you need to know, one word you need to know is a pulse. A pulse is a single vibratory disturbance, and I can draw it like this. A single vibratory disturbance would look like one crest of a wave that's moving forward, as opposed to a periodic wave, where a periodic wave, you got a crest, a trough, etc., and they're moving forward. Okay? So a pulse is one pump of a wave, and the periodic wave is successive ones. Now, when you're talking about the material or the medium, that's the material that the wave is moving through. There are certain waves that have to have a material. Those are material waves. Examples of material waves would be water waves. Without water, you can't have a water wave. I know that's kind of obvious, but it needs to be said. You can't send a wave through a spring without the spring. And you can't send sound through the air without the air. Okay? Now that one we'll come back to and we'll actually do a demo later, because it's not always obvious to people that you need air to send sound. And so I'll do a demonstration where we can take the air away and then the sound won't travel. It's pretty cool. But anyway, if you need material to travel through, if the medium is needed, it's called a material wave. The other version of that is called an electromagnetic wave. Now, electromagnetic waves have electricity and magnetism that alternates back and forth. And electricity and magnetism can travel through a vacuum. So you actually don't need the material. So if you're talking about a light wave, or a microwave, and I don't mean the thing that you cook, I mean the wave that's the micro size, or a high energy gamma wave, these things are electromagnetic waves. They don't need material. They can get from the sun to the earth with nothing in between. That's a totally different type of wave. Now, when you're actually looking at a wave, when you break a wave down, there's a way that the particles move. Or there's a couple ways that particles can move. Particle motion. The first wave is called, or first type is called transverse. Transverse waves are probably the most common, recognizable, and basically you have the material moving up and down or back and forth while the wave is moving forward. So this arrow up here represents the motion, forward motion of the wave, and this represents the vibratory motion, or the way that it's moving the material up and down. So the material is being moved up and down, but the wave is moving forward that way. That's called transverse. And if you take one particle, if I take one particle right there on the wave and watch it, just keep my eye on that one particle, that particle will go up, it'll go down, and it will return to its original position. Okay? As the wave goes by, it'll zigzag and return. Now the other version is called longitudinal. Now longitudinal waves are very hard to draw, but basically they consist of some compression and some rarefaction. Okay? So it's kind of like a caterpillar. Like a caterpillar goes like this. You're compressing, so this here would be compressed. And then you're rarefacting, or you're stretching. Okay? So you compress and you have a rarefaction. And that process moves the wave forward. A perfect example of this is the way you're hearing me right now. That's a sound wave, and sound waves are longitudinal, and longitudinal waves work like this. The sound comes out of my mouth, and the air is compressed and rarefacted until it gets to your eardrum, which compresses and rarefacts your eardrum. And then you're like, oh, I can hear. So that compression and rarefaction is the way you're hearing me. The example is sound, the easiest example for us to talk about. All right, moving on quickly to the next thing. I need to draw a real quick picture here of a transverse wave. And I'm just going to draw something like this. I'm going to go down, I'm going to go up, I'm going to go down, I'm going to go up. And I'm going to put a equilibrium position just to show you that there's above and below the equilibrium position. I'm going to label this A, B, C, D, E, F, G, H, I, J. That's probably enough. Okay? Now, one word that needs to be said is amplitude. Amplitude is how far you are from the equilibrium position. So, on this picture, where are the 2 points that have the greatest amplitude? On this picture, you're talking point C and point G. Those have the greatest amplitude, or the greatest separation from the equilibrium position, which is the middle. So, if they're looking for amplitude, you're looking to find the greatest separation from the equilibrium position, so that's C and G. Now the next idea is called in phase. 2 words, in phase. And if you are in phase, it means you're at the same point of the wave, but like in a forward position. Let me give you an example. In phase, if you took position, or point B right here, and you were looking for the in phase point, the in phase point would be when you're at the same spot again later on. So if you follow along here, that'd be J. Now some people get confused and they say, oh, can't it be B and D because you're at the same amplitude? But think about it, the wave is going like this, and at this point it's going up. This is like a down and this is like an upswing, so they're not the same. It's not the same again until you're back on a downswing and you're in the same amplitude. So if you're on the same part of the wave moving at the same direction and you have the same amplitude, now you're in phase. And the key with in phase, this is the really important part, is that in phase things are one wavelength apart. That's key. One wavelength apart in phase. You gotta know that. So when you look at the picture, if you find 2 points that are in phase, they are one wavelength apart. Now while we're talking about wavelength, the word wavelength we've defined as 2 points that are in phase, but there's a symbol for it, and it's a lambda. Greek letter lambda, like that. Okay? This right here is the letter that you will use to represent when you're talking about a wavelength. Now the other things you should have labeled on this picture, back to the picture for a second, is when you get to a high point, that's called a crest. And when you get to a low point, that's called a trough. So you have a crest and a trough of a wave. When you're talking about a wave, you can also say how frequently a wave is passing by. That frequency is the number of waves per unit time, or per second, let's say. Okay? Per second time. So it's the number of waves per second. The way we write this as a physics equation is F is 1 over the Greek letter tau. So frequency is 1 over the time it takes for a wave to pass by, 1 over tau. Now the units are 1 over seconds, but that has a special name. If you say 1 over seconds, you're not wrong. It's just that everybody else usually is going to refer to that as hertz. Hz. So hertz are the units for frequency. You have a certain number of hertz. And the last thing we want to talk about today is the period. The period is the time it takes for one wave to go by, which a lot of people confuse with frequency because it sounds really similar. Frequency is how often a wave goes by, and period is the time it takes for one wave to go by. So this is usually a really short amount of time. But the cool thing is, you don't have to really learn a new equation. If you take this equation and rearrange it this way, so tau is 1 over f. Tau is the period. Tau is the time it takes. So if you take 1 over the frequency, you will get the period, or the time it takes for one wave to go by. So for today, that's the basics of waves, physics.